the axially loaded bar deformation, we usually write like U is equal to PL by AE. Let's say this is the deformation of the axially loaded bar. Okay. Yeah, you know that now this same formula can be derived from this minimum potential energy principle also. Okay. So now let us see how do you derive the same formula both from the fundamental stress strain relation as well as minimum potential energy principle. Okay. So this is very simplest case that you can understand how you apply minimum potential energy principle. Okay. Now consider a bar which is axially loaded, like with a load P having this the length of the bar is L. Okay. One is fixed. The other end you are applying the load P. Okay. So first let us apply the simple stress strain relation to get this formula. Okay. Okay. So stress divided by strain is its modulus. Okay. So now what is stress for us? It is P by A. Okay. Load by area. What is strain? Change in dimension by original dimension. For example, after you apply this load, let us say the bar has elongated this much of amount. Okay. U. So this is the elongation. Okay. Nothing but deformation. Okay. So this is the change in dimension by original dimension is the strain dimension. Okay. Now you substitute these two in this expression of stress strain relation. Okay. So now E is equal to stress means load by area. Okay. Divided by strain means U divided by L. Okay. So it goes like this P by A, EL by. Okay. Now what you want is deformation value. So send U to the left hand side and E to the right hand side. So it is PL by E. So this is the deformation formula that you have used for axially loaded bar case. Okay. The same thing you can easily get it by applying minimum potential energy principle also. Okay. So that we will see how it goes. Okay. Say consider now the same bar. Okay. I'm going to consider the same bar again. So let us draw the bar. Okay. So now I first need to write what is total potential energy of the system. So it is nothing but the internal strain energy plus the external work done by the forces applied. So this is what is the total potential energy of the system. So first let us write the strain energy stored in the bar. So it goes from the basic formula half into stress into strain into volume. Okay, the basic simple formula. So half into stress, again I can write it in terms of strain into x minus into the strain term is already volume. It's like a uniform prismatic bar, so transaction area is same throughout. So A into L will give you the volume. Okay, so half into Young's modulus into strain, I can replace it with U by L. This whole square into A into L. Okay, so this is what is strain energy stored in the bar. So let us simplify half into E into U square by L square. A into L. So L goes here. So what I get is half into E into A U square by L. So this is the strain energy quantity that is stored in this part. Now the work done, okay, is equal to minus force into the displacement that is happening at this end. So this is the displacement happening. So P into U is the external work done by the force. Okay, right. So now let us apply this total potential energy principle. Okay, so pi is equal to U means half into L A U square by L minus work done P into U. Okay, now apply the principle. Okay, so what minimum potential energy principle says is like dou pi by dou u shall be equal to 0. Okay, so in mathematical form, we have already explained what is the principle in theoretical form in the previous video. Okay, so now you apply this. Okay, so partially derivate this potential energy with respect to u and equal it to 0. So what you get here, half partially derivating u here, A half into E by L. These are all constants. So u square, dou u square by dou u is nothing but 2u minus P is a constant. Dou by dou u of u is 1. Shall be equal to 0. Okay, right. So this 2 goes here. So what you have is A u by L minus P is equal to 0. Okay, right. Now we want u value. So rearrange this equation. A u by L is equal to P. Take P to the left hand side. So now u will be equal to P L cross multiply. Okay, divided. So this is how you derive the same equation for the deformation of the axially loaded bar PL by A from the minimum potential energy principle also. Okay, so this is how best you can understand the minimum potential energy principle application. Right. Thank you. We'll see you next video.